In this session, we will consider, we'll cover a small review of set theory, which is necessary for building our theory of probability. But first of all, what do we mean by probability? So you have the Bayesians. They have one way of looking at probability. You have the frequentists. They have another way of looking at probability. Probabilists and statisticians probably see probability a little bit differently. And the philosophers may also see probability in a different way. And so we won't get into that. I won't actually define what probability is in the vague general sense. We will talk about probabilities and what those are, how you define a number that you call the probability. Okay, but what's the idea of it? Why are we trying to do this? Well, because everything, real life, let's say, involves uncertainties. Okay, so for example, if I'm driving a car, I might get into a traffic accident, right? And so it makes sense to wear a seatbelt, right? There's another possibility, and that is that this entire LUMS campus could be destroyed by a meteorite. Maybe if I'm worried about that, I would try and get a job underground. But somehow these two possibilities, these are two events that could happen. They somehow feel different to us. So what's going on there? Right? Every possible event is not equally likely. And so we might think of probability as a way of assigning numbers which affect the likelihood of an event. Okay, so if an event is absolutely unlikely, if it cannot possibly happen, then we would assign it a probability of 0. And if the event is certain, we would assign a probability of 1. Okay, and we need ways of assigning probabilities that are in between. And to do that, we need to develop a mathematical way of quantifying the likelihood of events. Okay, and with all mathematical subjects, at the base of whatever it is that you're doing, there are sets and there are functions. So I'm just going to review a little bit about sets, just that little bit that we need to develop our theory. Okay. So what's a set? Well, we don't define it. It's a basic notion. Informally, a set is a collection of objects. So, and the members of a set are called elements of that set. So, for example, A is the set of all students registered in this course. Each student is an element of A, and the course instructor is not an element of A. Okay. And this is the notation. We read this as small a is an element of the set capital A. And if I want to say that small a is not an element of A, I put a stroke through the symbol, which means element of. So this reads, A is not an element of A. Okay. There's a set that also comes up a lot, which is called the empty set. This is the set which has no elements in it. So the notation for that is either curly brackets with nothing in them, or this Norwegian letter which looks like an O with stroke through it. Okay. Both of them are then called the null set or the empty set. Both are notations for the null set or the empty set. Okay, subsets. We're going to talk about those a lot. So A is a subset of B is the same as saying that every element of the set A is an element of the set B. And this is the notation. We read this as A is a subset of B. Okay, so some examples of subsets. A is a subset of A because every element of A is in A, trivially. And we take as an axiom that the null set or the empty set is a subset of every set that you can imagine. Okay. Equality of sets, we say that sets are equal. A is equal to the set A is equal to the set B if A is a subset of B and if B is a subset of A. Complement of a subset. So let's say we have a set S and we have A as a subset of S. Then the complement of A with respect to S is the subset of all elements of S which are not in A. Okay? So here's an example. Let's say that my set S here is the integers. This Z over here stands for the integers. So A is a subset of the integers. And A consists of the numbers -1, -2, -3, and so on. So what are the complement of A with respect to Z? Are all the elements of Z which are not in A. Everything which is in Z which is outside of A that's the set that we're looking for. Well, 0 is not in A, but it's in the integers. 1 is not in A, but it's in the integers. 2 is not in A, but it's in the integers. So the set we're looking for is the complement of A with respect to Z consists of the integers 0, 1, 2, and so on. The subset of set. Okay, so for the notation, people either write A with a dash, A prime, for the complement of A, or they write A with a superscript capital C for complement. I'm going to try to be consistent and use this dash. But if I slip up and I write C by mistake, then it means the same thing. A superscript C and A dash are the same thing. Okay, so the definition for A complement with respect to S, so A is a subset of S, and A prime consists of, A complement consists of all those B which are in S, with B being not an element of A. Okay. We have the idea of an intersection of sets. If A and B are sets, then this notation here means intersection. The intersection of A and B is the set which contains elements which are in, all the elements which are in A, and also at the same time, they are elements of B. So the intersection of the positive integers and the intersection of the negative integers is the null set, for example. Union of sets. So we read this terminology as A union B. So A union B, or the union of A and B, consists of those elements X which are in A, or they are in B, or they are in both at the same time. Okay. So example, the union of the positive integers and with the negative integers is the set of all integers except for 0. We should know a few rules for involving unions and intersections. We'll need these for deriving some of our results. So it doesn't matter whether you write A union B or B union A, it's the same thing. And it doesn't matter whether you write A intersection B or B intersection A, that's the same thing. So these are commutative laws for sets. Associativity, it doesn't matter whether you take the union of B and B with C, and then you take the union with A, or you take the union of A with B, and then you take the union of C. Those are the same things. So it's an associativity law. Okay. Same thing for intersections. The intersection of A with the intersection of B with C is the same as the intersection of A with B with intersected with C. Okay, we'll need distribution laws also for our for deriving some of the results that we need in this course. So A union B, if you intersect that with C, you get A intersection C union with B intersection C. And if you take the intersection of A with B and you take the union of that with C, then that's the same as taking the intersection of A with C and intersecting that with the union of B with C. And so you have these distribution laws. And we have De Morgan laws. The complement of the union of A with B is the same as the intersection of A complement and B complement. And the complement of the intersection of A with B is the same as the union of the complement of A with the complement of B. So these are De Morgan's laws. Okay, we need these. Sometimes it's easier to find a probability associated with a set by first finding the probability associated with its complement. Okay, and a bit of terminology. This helps us now to connect sets that we've been talking about with probabilities. An experiment is any random process that generates a set of data. We call that an experiment. Our experiments are going to be different than experiments in, say, the chemistry department. Our experiments are all going to be thought experiments. Okay. So here's an experiment. You shouldn't, again, it's a thought experiment. We would never do this in real life. Okay. So you're in the classroom, the instructor throws a blackboard eraser. If it hits someone, record a hit. If it misses, it doesn't hit anyone, record a miss. That's an experiment. And it's probably random, right? You're not guaranteed always to hit exactly the same student. Okay, so now, what are the outcomes of this experiment? Well, the outcome of the experiment could either be a recorded hit or a recorded miss. So what's important in this course, quite often, is the set of all of the possible outcomes. So in this case, the set of all of the possible outcomes is the set which consists of hit and which has elements hit and miss. Okay, and the number of elements in this set of all possible outcomes is 2, right? Hit and miss. There are 2 elements in this set of all possible outcomes. Okay, let's try another experiment. We're going to roll a fair die, and we're going to record the outcome. Okay, so what could the outcomes be? Well, the die is labeled with dots, the outcomes, and then there are 6, it's a 6-sided, well, I should have said it was a 6-sided die, but if I don't specify, and I just say a fair die, I mean a fair 6-sided die. Okay, so what are the possible outcomes? You could, well, the set of all the possible outcomes, you could roll a 1, a 2, a 3, a 4, a 5, or a 6. And there are 6 elements in this set of all possible outcomes. And usually we use, in this course, we will be using capital S as the set of all for the set of all possible outcomes of an experiment. Okay, here's another one. It's a little bit different. Supposing we have an electronic device, let's turn it on. We have a stopwatch, so when we turn it on, we start our stopwatch. And we see what happens until we see how much time it takes until that device fails. Okay. So what are the set of all possible outcomes? Well, it could fail as soon as we started, so it could fail at 0. In principle, it could just keep going. I mean, it won't, but in principle. The set of all possible outcomes here is an interval of real numbers running from 0 to infinity. Infinity isn't a real number, right? And we say that then the cardinality of this set, the number of elements in this set, is infinite. Okay, so just a little bit of probability review. Sorry, a little bit of set review. Now let's start connecting our sets to our experiments. So sample spaces and events. So this set S that we were talking about before, the set of all possible outcomes, we're going to call that the sample space. And like I said, we're going to use capital S for sample space. So the set of all possible outcomes of an experiment is called the sample space. Events are subsets of the sample space. Okay. So let's go back to the experiment that we had. Roll a fair die, roll a fair 6-sided die, and record the outcome. So what was the sample space? We already saw this. This was a sample space, and it had a cardinality of 6. Some events associated with S. These are the subsets of S. So one event could be that you rolled a 1 or a 2. So that's this set A. This set A, we call that an event. It's a subspace. It's a subset of the set of all possible outcomes. Another event B, that's when you roll a 2 or a 3. So rolling a 2 or a 3 is regarded as an event, as a subset of the set of all possible outcomes. So B is also an event. Okay, again, we power up an electronic component, see time till failure. We saw that the sample space was the interval from 0 to infinity. And an event would be a subset of the sample space. So if the thing that you would be looking for, the event that you would be looking for in this case, is does it fail between 1 and 10 time units? So that's the interval, the closed interval from 1 to 10, right? So this is an event. Okay. It's a subset of all the possible outcomes. Okay, and the complement of an event A with respect to S, that means all the elements of S which are not in that event A, which are not in that subset A. Okay. So back to rolling the fair 6-sided die. This was S was our sample space. A is an event rolling a 1 or a 2. B is an event rolling a 2 or a 3. And what's A complement? Everything which is in A, which is not in S. B complement is everything which is in S, which is not in B. Okay. So see, the outcomes which were not in A are rolling a 3, a 4, a 5, or 6. The outcomes which are not in B, that is B complement, that's rolling a 1, a 4, a 5, or a 6. Okay, so we said, let's power up an electronic component, record the time till failure. S, the outcomes of this experiment are the interval from 0 to infinity. A was the interval from 1 to 10. So the component fails somewhere between 1 and 10 time units. And now what is the complement of A? So that would be anything which lasts from 0 to 1, not including 1, and anything which lasts from not including 10 up to infinity. So that's what A complement looks like. Okay, and that's also an event. Okay. Intersection of events will be important for us. You're saying when both events occur, right? In an experiment. So A intersection B means those elements which are in S, which are in A, and also at the same time are in B. So we roll a 6-sided die. This was our set of possible outcomes. And these were two events, A and B, that we talked about. What's the intersection of A with B? The elements which are in A and in S at the same time. That intersection is rolling a 2. Okay, so back to the electronic component example. We have a sample space that goes from the interval from 0 to infinity. If we had an event, the component fails between 1 and 10 time units. Another event is that it fails between 11 and 30 time units. Then the intersection of those two events is the empty set. Right. There is no element which is in both A and in B at the same time. So that intersection is the empty set. Okay, so in probability for such events, we use the term mutually exclusive or disjoint. Right? So events A and B are mutually exclusive, or they are disjoint if A intersection B is equal to the null set. Union of events, we already defined that. It's the set which consists of elements in A or in B or in both. Okay. So the dice rolling experiment, you get results from 1 to 6. That's your sample space. You have the A and B that you had before. Now the union of those two events, A union B, consists of everything that's in A, that's 1 and 2, everything that's in B, that's 2 and 3. So A union B is rolling a 1, rolling a 2, or rolling a 3. Okay, so back to the time till failure experiment. All right, if the time till failure is 1 to 10, that's one event. Another event is that the B is that the time till failure is from 5 to 30. And if I take the interval, if I take the union of those two intervals, then I'll get 1 to 30. The union of A with B is the event that the time till failure is between 1 and 30 time units. Okay. All right. So that was a brief review of the set theory that we are going to need in this course.